So because we're pulsing it right at the resonant frequency,
with the maximum impedance, the question is can we tap into any of that induction voltage?
would be a good thing to find out.
I kind of want to tune it to a slightly off frequency.
And see what happens when you adjust it up to frequency.
Yeah, see if this, see what happens. Yeah. Because actually, we need to put a current probe somewhere, but this giant magnet doesn't allow me to do that very well.
Yeah.
That's fine. We'll run a lead all the way over
Why
here.
did you let that guy in Cincinnati buy you such powerful magnets? You should have had him buy some cheaper ones.
That guy, I don't know what his problem is.
He's a slacker.
Just big magnets. I don't know why he would do that. Huh? Hey, that doesn't need to charge. Yeah, use the black one only. Thanks. Okie dokie. We'll just use the blue one, I guess.
Way over here.
That's crazy. Let's see if it's the right way. We'll just shield it up. It is using like negligible. That's crazy. I can't even tell if it's the right way. Let's see if we can get closer, I guess. It just rings. What is going on? That is bizarre. This is pulse time, that whole section right there. I think that's right. Up should be positive.
Yeah.
I think that's right.
Cool.
Alright, well let's shield it and zero it out. This worked well. I need to build a cage so that I can do this easier.
Plastic, yeah.
I wonder if I could put this whole probe in a tin can and run the wire through if it would work. I need an open in though, don't I?
Yeah.
You know what I mean? I can't put this wire through this hole without inducing into that metal.
Yeah.
That's what I mean.
Yeah.
Hello, my dear.
What are you working on?
We got the switches in that Richard ordered, and so we're
back on the cheesy fan.
Cheesy wheel.
We're back on the cheesy wheel.
Cheese wheel. Because cheese come in a wheel.
But this is a fan blade, so it's a cheesy fan.
I like my cheese wheel, baby.
Yeah.
Cheese fan.
What's really funny is my aunt's been talking about Swiss cheese on Facebook.
Yeah.
She's like, Mary Lee, I can't believe you introduced me to Swiss cheese finally. It's so amazingly yummy.
What? She's never had Swiss cheese?
I guess not.
I like Swiss cheese a lot.
I do too. And I said, wait till you try Lacy Swiss. He said, that's my favorite.
I like the baby Swiss. Well, that's good.
Baby Swiss is very similar to Lacy Swiss.
Oh.
It's really good.
Well, that's ridiculous. Okay.
I like Lacy Swiss, and then I like the really strong, thick slice Swiss cheese just to eat a slice of. Oh, it's so good.
I can just take a big block of Swiss cheese and cut off a big chunk and just eat.
Oh, I can't do it that way, but I had to have it sliced, because then it's too much, but I like it.
Okay.
Are you live?
Yeah.
It's like a mouse. Yaw, yaw, yaw.
Oh, yeah. It doesn't even move.
Yeah.
Well, I guess it can't. It has no reason to move. But...
Sorry, I couldn't hear you.
It has no reason to move, I guess.
Oh.
Is this the new cappy thing you bought?
Yeah, it's a...
Black thing?
It's like that. but smaller and pulsed by a coil. So it's a little different.
What is it? Holds the energy?
No, it switches it.
It's
a switch.
It's just a switch. Turns it on and off like a light switch.
Oh.
But it does it really, really fast.
Very cool.
Yeah.
Read.
$27 worth of coin.
Yeah.
I can buy a pair of shoes with that money.
I know.
That's crazy. Too bad you can't make your own.
There were 2 of them for $27. So.
Still a lot.
Yeah.
Okay, so this is interesting.
Yeah.
So if I stop it,
Yeah.
let it sit, those current spikes, well, now they're not mostly positive, they're kind of all over the place.
Right.
But when we spin it, they're very well directional.
Yeah.
So there's definitely more current flowing.
Something happening, yeah. Something's definitely happening.
Something right there is happening.
Captain Obvious speaking, sir.
Captain
Something
Obvious.
definitely happening.
Oh, it's like totally random. I guess I need to put that resistor back in the line and make sure these are proper measurements. Cause it's like, I guess that's okay. It's just random, you know.
Yeah.
It's a bit more random than I would expect it.
Yeah.
Now, I've seen randomness on this probe. You gotta be careful with it. What is that? That's 20 milliamp spike right there. I guess that makes sense if it is possibly charging and throwing a discharge across
I
there.
don't know.
Richard don't know.
I don't know.
And I don't either. But we're gonna find out.
Let's find out.
Oh yeah. I have no idea, but it's definitely on top of the switch. Now I did want to change the frequency now.
Alright.
That was one of my to-dos. I wanted to see if doing quarters has changed this dramatically.
To do or not to do? That is the question.
Always do. Alright. What's half a... No.
Does it depend upon the rotational frequency? When you spin it, does it do anything different when you do spin it faster as opposed to slower? Or,
You mean the current?
just curious. Yeah.
I don't know. It just seems like it happens
Yeah, random.
at a faster cycle.
Okay.
There's like... a little bit of...
Yeah, there's something happening on every pulse.
A little bit of something going on there. So here's on switch. And then I guess it switches off and tries to finish its cycles, what it's trying to do, it looks like. You know what I mean? Because if it wasn't there, it'd be way up here.
Yeah. Let me change frequency and see what happens.
Yeah, it's trying to finish its pulse. Oh, that's terrible. Alright, we'll see if it changes anything. Okay, we're 5.3 kilohertz. Let's go down. So now we're switching like way down here. Do you hear that? Do your ears pick that up? You can hear that.
Ringing, just like the light switch.
You know when you have two different audios?
Yeah, beat
That's
beat
what
frequency.
it's doing, yeah.
Really?
Yeah, I can hear it.
Wow.
You hear it?
Mm-hmm.
I don't know exactly where I hear it from. Oh, it's definitely the coil.
Well, really?
Yeah.
Oh, that's awesome.
That's crazy.
Wow.
Oh yeah, you can see it there.
Yeah. Oh yeah.
You can hear it because you can even see it here.
Wow.
That's wild.
Cool.
There it is.
Look at that. Oh my goodness.
That is wild.
Maybe you could extract the energy in an audio form.
Well, we're starting to look like Myers circuit. Maybe we need to put a water fuel cell across it. Pooch, what's the other guy with the other? Can't say his name very well.
Iron D-Max?
No. Original people, not us.
I don't know what you're talking about. I don't remember right now.
You got only the few.
Excuse me. What?
You got only the few. You got Meyer, then you got his brother, and then that other guy, the guy before him.
Oh, I don't remember.
Puchos, or I can't say his name.
I don't know how to say it either.
Anyway, this looks more like what he was doing.
Yeah.
I can hear that. That's pretty crazy.
Yeah, it is.
I can very clearly hear that, actually. So it's like, when it gets past the breakdown voltage, it appears, because that appears probably like the breakdown voltage. Whoa, 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 whoa. Go back. There we go. We're going to measure it. What's on 100 volts per division? 1, 2... Oh, it's offset though. If that was 0, 1, 2, yeah, 250. That's like the breakdown. Because those peaks right there are.
I would think it would go flat top if it was hitting the breakdown.
But it's discharging. Boom, 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 boom. See it? See how it starts going up?
Yeah.
Hits a breakdown, then it just constantly discharges till it comes back.
Till it gets back.
Yeah. Makes sense.
But look. Every other one's offset. That one's up, that one down, up, down. What's that?
North magnet, south magnet, north magnet, south magnet. All the inductions going this way and all the inductions going that way. So even though we're at 0, it's offset.
Yeah.
Offset, 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 offset.
Cool.
You can't hear that, but I can hear that. And you can see it. Listen real close.
Yeah, I hear it now. Yeah.
That is pretty interesting.
Yeah.
I guess I'm hearing this frequency switching. Oh, now it's dragging.
Is it?
Yeah.
What did you do? Slow down the frequency of the oscillator?
Yeah. Like.
Man, that's dragging.
Cookie?
Okay, thanks.
Found one, huh?
I did.
Wow.
You want some?
Fancy cookie.
Okay.
It's the good kind.
Thank you.
You're in the frame.
Sorry.
I just don't want that stuff public if you don't want it to be. Whatever it is. Okay. So now the question becomes, can we operate it this way?
No.
Probably not. It probably won't run.
Probably not. But if we're spinning the shaft with some other device.
Oh yeah, that's a whole other question. Yeah. Okay. Can we take that out?
Exactly.
So let's charge cap. I can only charge cap unless if I use a diode, or I can use the switch at the right time. I have the choice, right?
Yeah.
I don't mind using the switch. It's pretty easy to do. Okay, that's a good question. Can we do that?
I don't know.
Because that would be pretty interesting. I mean, there is 0 resistance there.
Yeah, and if it'll charge the cap, I mean, that'd be like, wow.
Now that would be like, wow. The question is how fast, because we've learned that is a big dilemma.
Yeah. But remember, this is a pretty small device, actually.
Well, yeah, but I mean,
Yeah.
like the time it took
Oh, right.
and the amount of
Energy
quote
put in.
unquote,
Right.
that was our issue, or our
Right, I know.
thoughts
We
there.
had to measure energy in versus energy out, or run it off the capacitor.
Well, look, I took the battery off. Let's just hook the probes up to the meter and see what it looks like.
Alright.
Like if it's... Okay, so it's on 50 volts, so we're inducing... No, 70. We're inducing 75 volts right there.
Yeah. That's not
So
bad.
so the induction is there,
Yeah.
right?
And still zero resistance, right?
Well,
Yeah,
it's open.
Yeah.
If I short it,
Yeah. It's free.
that's crazy. That is really wild.
Yeah.
It is like at the highest impedance. So I wonder if there's going to be any current going.
I have no idea.
Because if it can't flow, it can't get out. I mean,
Yeah.
you know,
I don't know, buddy. I don't know.
that's pretty weird. All right, I'll just use a diode in this case.
Those buttons are in California.
Amazing. When was that taken?
January 9th at 6:17 p.m. on ABC News.
That's cool.
It was recent.
So let's say we want negative to go. Oh, I need to put that probe on the cap. Either way, this needs to go to the negative. This needs to go to the coil. Guess I should turn that off. If I'm not using it, I only get 4 hours of runtime for $12 at this frequency.
That's all right. I don't care. I'll buy another.
That is insane how
I'll
bad
buy-
we can break this so fast if we're not careful.
I'll buy another one. It's no big deal.
I looked it up. It was a 10 to the 5 switching cycles.
And the vinyl.
Yeah, so 10 to the 5 at 5 kilohertz. How long do we last? You need a calculator?
Yeah.
You probably don't.
Yeah.
'Cause you're a slacker.
20 minutes.
No! No! Oh my god! Really?
But I think it'll go a lot more than 10 to the 5.
Probably, because we're just flicking it back and forth. I think that was at 50 watt load.
Yeah.
Or something like that. 20 watt, 10 watt load. But still, that's insane.
Let me make sure I'm right here.
That is crazy. Do I have this right? I have no idea. Oh yeah. It's on the wrong side, whatever it is. That is crazy. Oh. Okay, we got this side going through that to the positive. What am I doing?
20 seconds. So it's
What?
Yeah, there's something wrong.
I think it said 10 to the 5
10 to
if you're switching 10 watts. No, if you're switching 50 watts. And then if you're switching 10 watts, it was 10 to the 6. So if we're switching almost nothing, theoretically our switch life should be going more.
Yeah.
Right?
I have worn out reed relays before.
Really?
In a data collection lab that I designed years ago. I designed a data collection lab for RWGresearch Associates, and Pratt & Whitney, and GE, and one other company all inspected it, said it was the best metallurgical creep laboratory in the world. Yeah, I designed the best laboratory in the world.
That's amazing.
Yeah.
You're such a smart guy. That's amazing.
That was years ago, but my uncle came to me and said, well, he came to me with his son's stereo and asked me if I could fix it. And I fixed it. He said, I've had this thing to 3 different shops and nobody could fix it. I said, oh, it wasn't that hard. He said, would you like a job? He said, you know computer stuff, right? I said, yeah. He said, would you like a job? So I said, yeah. So
I said, yeah.
So he gave me a job in his computer department, programming the computer. One day I ran into him in the hall, and he said, man, we really need to update our lab. I said, well, I can do that. He said, you can do that? I said, yeah, because he was the owner of the company, and so he gave me reign to do it, and I did it. It took me a year and a half, but it was the best. And the other vice presidents of the company were all losing faith. They said, well, this guy's just burning up money and whatever. But then after it was done, it was like really,
It was like amazing.
Yeah, it was amazing. Yeah,
That is cool.
I invented I invented it. I don't know if anybody else invented it or not, but I invented a method called data-driven data collection, whereby I only took data when the data changed by a certain amount. So I never missed any data. If the data started changing fast, my collection rate just skyrocketed. If the data was just barely moving, my collection rate was way low.
Okay.
So it was data-driven.
Right. That would be very logical, wouldn't it?
Yeah. For me, it was logical.
That would be very logical.
At the time, nobody had ever heard of that, and so they were always the creep tests could last up to 5 years. So they would set the data rate real low because they had to take data for 5 years, and then when it would start moving, they would miss the curve, and so they would have the thing, and then after 5 years of tests, they would miss the curve. So I invented a way so that they would always capture it.
That's amazing. Richard's a pretty smart guy.
I know he is.
He's a really, really, really smart guy. You're a really smart guy.
I don't know why I'm talking about myself. I never talk about myself. You guys bring out the worst in me.
Oh, it's good to talk about yourself.
We're good about that. There it is, charging up.
Cool.
It's minimalistic, but can I go faster? And yeah, it is. Faster I go, the more charge. That's going to be really hard to quantify.
That's 500 microfarad.
Yeah, that's going to be really hard to quantify.
Yeah.
I can put a smaller one on there. I put this. Oh, it's got all the meters across it too, so it's
it's fighting against the
it's
meters.
actually discharging already. See it?
Yeah, it is.
What did you say, my dear?
I don't know.
All right. I don't know either.
I don't think I said anything.
Okay.
If I were a rich man.
If you were a rich man, I'd be at your house every day. Boo.
You wouldn't have to. I'd just send you money.
If you were a rich man, I would just have you send me money. Oh, wow. You remember when we tried to charge that up to a couple thousand volts?
Yeah.
I think it took a lot more effort than that.
Go get a jacket.
Yeah.
At zero.
Counter by the
Yeah.
dryer.
That is interesting. Look how fast it's discharging across the meter.
Yeah.
You need to cut your hair a little bit.
That's really cool.
Yeah.
No matter who says what, we've theoretically eliminated
All resistance.
all resistance
Yeah.
in the rotational.
And
We can't quantify that right now because
Yeah.
really there may still be some, but
Right.
that's pretty darn amazing.
Yeah.
It's a drawing
It is.
Daddy did.
Maybe you should make a little quick shot of that.
All right, I'll do that.
That's a daddy question.
Just curious.
I should do that.
The fact that it's even producing anything with such low shaft resistance is pretty phenomenal.
You know what we need to do? We need to spin it up. We need to calculate the time for it to quit. Then we need to spin it up and do the same. We can actually do that by measuring the rotational frequency.
Okay.
You are.
Well, that's exactly what we're going to do. That'll give us a quick
All right.
quantification at least.
All right.
A little bit.
Okay, cool.
You know what I mean, right?
I know.
Again, spinning it towards me.
Being captured.
It's capturing it.
I mean, you've been personally captured by Lily.
Yes, I have. Okay. So we're going to take a window of this.
Are you supposed to get snow this weekend in Ohio? Are you supposed to get snow this weekend in Ohio?
I have no idea. I haven't looked at any weather
Well,
reports.
there's a huge snowstorm coming this weekend, so I was wondering how far off it's going to go.
I should be home by midnight tonight.
Okay. I don't know when it's supposed to hit Evansville, but
Oh, I don't know.
yeah. It's not going to be a lot. I think they said like 3 to 8 inches or something like that.
Well, I hope I make it home.
Yeah. You should. I don't think it's supposed to hit till tonight. As far as hitting Evansville. You're a little bit of ways.
Yeah.
4 hours or so.
Yeah. From Evansville?
Okay, 300 to 100 volts.
Yeah, I think about 3 or 4 hours.
Lily, did you go potty?
No, I don't do it.
Did you toot?
No.
300 to 100
Are you
volts.
No.
So what I'm gonna
Do you have
do,
cookie in your underwear?
I'm gonna measure the
You have to
time
be
real
on.
quick.
That's a nice wave, though.
Yeah. What?
No.
300 to 100 volts, that's 200 volts. What's 0.85 microfarad?
Yeah.
0.000.
Oh no, I can't do that. Oh, that's difficult. Alright, well, we'll just get a best guess here.
That's 170 microcoulombs.
Okay. That's 13 seconds. Towards me. Alright. I'll do it again.
Okay.
Lily, what are you doing?
This chair over here.
But I'm gonna turn it on when it hits.
Mom, I need this space.
I can't do the space.
I'm gonna move it.
Oh, I need to measure it a different way, I think.
There you go. Not too close, not that close. Let's sit right here. Knock the wires off.
Okay, so when I turned it on, look what happened.
Yeah, it went shooting way back up.
Because it had voltage across it. But that's okay. Let's look at something here. Let's just do it where we started it,
Okay.
and then where we ended it. At the same voltage.
Yeah.
There's 13 seconds.
Wow.
Didn't
It didn't affect
it might have been a little bit different here because I got
might not exactly, but yeah, but it's close to the same exact amount of time.
pretty darn close.
Yeah.
I mean, we would have seen a.
Yeah.
Well, here, if I remove the switch and I just hook up the cap,
When you hooked up the cap, it dropped.
yeah, it did. Our cap got to a higher voltage. See how much higher it is?
Yeah.
But what is the time? Okay, now it's slowed down by, we'll call it, I don't know, 8.5 seconds.
Yeah.
But our coulombs was higher.
Yeah, because the voltage was higher.
I'm gonna run it again with the pulsar to see what the voltage was actually at. So during that time frame, the voltage was off the screen. So 50, 100, 200, and no way, 250 volts. Is that 50 volt per division? Okay, let's change the cursors and see where it's at. Yeah, it is. Oh no, 150 volts is off the. No, it's not. Okay. 250. It was over 250. I don't recall seeing 250 there. I'm gonna have to do that again. I want to look at this meter down here. Oh, it was all the way past 250. Alright, well let's try it again with the generator. So now we should can include that number, I guess, but I went up to 130 something. So in order to do that properly, we need to determine a few more parameters. Look at that though, it charged up only exactly to the voltage it was at.
Yeah.
It started and didn't go past. It's kind of interesting in itself. Look at that. It was at the ring was at 300 volts and the charge started at 150, so that's half.
Yeah.
That's an interesting thing.
There's some interesting effects going on here for sure.
Oh yeah, stuff that we normally don't see.
You should take a photo on your phone of that.
It's all on the stream, but
Oh, never mind.
I can still take a photo.
You don't have to.
Watch me. I'll take a photo. Boom. Photo has been taken. Okay. Anyway.
It was just an idea.
Here, I want to see.
You don't have to
I want to
listen me.
see.
I'm just kept it obvious.
I want to see what happens again when we do this.
And it goes down when you connect it.
Well, I mean the maximum right there. You know what? It's almost like try something a little different here. Okay, I'm gonna do this again. I'm gonna do the same thing. So our cap voltage is around 150,
Yeah.
and our induced is approximately 300.
Yeah.
So it's almost exactly half.
Yeah.
Wait a minute, B's at 75.
What's B? What's B?
B is
Cursor,
the top.
75.
Yeah.
And A is 150.
Yeah.
So it's
300
Yeah.
scales off by half. I could just scale it the same.
That's alright.
Here, there we go. Well, I'll leave it back where it was real quick. So 75.
And 150 is still half.
No, 300 at the peak.
And the cap was only charging 75.
And that was with pulse. Yeah. Right. So now if we do it without the pulse, at the same visual voltage here.
Yeah.
Oh, it's like Alright, so when the cap was at the approximate same 75,
Yeah.
then this voltage is only 76. It's almost 1 to 1. So the induced is exactly the same as that. So 70.
Without the pulse.
Yeah, so 75. 75. So basically, and I was rotating it
Much slower.
much slower.
So what's that telling us?
It's telling us it took less horsepower to charge it to the same voltage. Because I wasn't spinning it as fast.
Without the pulse.
I don't know about the RPM. It was definitely slower.
Yeah, definitely RPM was much slower.
But I can't quantify the torque really.
Yeah.
I really can't do that because we know it slows down a little faster.
Alright.
So we know torque is probably a little bit more.
Yeah.
So this would be really hard to actually measure properly.
Yeah. Yeah.
It can be done though.
Yeah, you have to have a DC motor that you can measure how much power you're putting into the motor.
We can do that. We did that already. We can do that again.
Oh, well, I don't know if we have time. What time is it? 11 o'clock.
It's 10:40.
Daddy.
Yeah.
Thank you.
Oh, you are so awesome. I'm gonna give you a point for cleaning up my shop.
It
Good job.
is the garage.
It's
Okay.
a garage.
Okay. Alright, it is the garage. My shop is the garage. This is
Garage
correct.
shop. Why don't we have a Ferrari in here we're working on? Or a Tesla? If it's a garage.
Can't answer that. If I put this on here.
That's not very smart.
Oh, thanks. Appreciate that.
Found it under the couch.
Good job. I'll put that right there. Alright. That's a busted resistor. Oh yeah, look at that. I mean, the voltage is going up, but I got a lot of torque.
No pulse. Yeah.
Yeah. So now if I discharge that. That was about 20 volts, not quite. Actually, where was that? That was maybe... We'll call it 25. We'll call it 25 volts. Now with the switcher. Although there's no resistance, the charge time is like super terrible.
Yeah.
But if I go faster, it's still more input. There might be a timing too here that we could do better at this.
Yeah.
So like if I went with half of 5.3, that would be 2.6 something.
And 2.65.
Now it's charging a little better, but I can feel a little resistance.
Daddy.
Yes?
Good job.
Oh, this is okay. Let's take a few minute break here.
Okay.
I gotta go to the bathroom.
Alright.
I'm gonna think for a second.
Daddy.
Yes. Great job, Lily. It looks so good in here. You did so good. You found all the pieces I missed. Give me 5. Give me that 5. Positive peak. Peak positive. Alright, I want to see if we can get to that frequency. Just go up a little at a time. I'll put my 9-volt back on there, I guess.
$66.25.
66.25. $66.25. Okay, let's see if we can switch at $66.25. What? 66.25.
Or you want to do third? You want to do 1/4, or you want to do?
Yeah. So it would be. It'd
Well,
be
one-
5.3 times
Divided
2
by
divided by. I do it differently, but yes. 5.3 times 2 divided by 4. Right?
That's half.
No, it's not half divided by 4.
Yeah.
That'd be a quarter.
5.3 times 2, though. Why are you doing 5.3 times 2?
Because I'm at 1 cycle right now. I don't know. Just
Yeah, it's
throw me a number. I'm
5,300 divided by 4 is equal to 1325. That's a quarter cycle.
No, it needs to be going up. We need to multiply that. Here. That's not right.
It's right.
No.
You're confused.
Because I need to go faster, not slower.
Well, then it's 66.
Oops. I'm lost. Okay.
Okay, from here to here is 360 degrees, right? That's 1 cycle. Right now, that's 300, right?
Yeah, and so in order to have a quarter of that,
It's
I need to have.
you know,
I need to
a
have
quarter-
a. I need to have a
quarter more.
frequency. No, I need a
That's-
tighter frequency, not a bigger frequency. I need a higher frequency. It has to be higher because I'm trying to get over here, not over there.
Trying to get over where?
Look, if I go down,
Yeah.
then I get more rings.
Right.
I need to go past that so I get
All right.
my half.
Why don't you want to try 66.25?
Okay, 66.
I don't know if it's really go much faster than that. It might. If you want to go.
But that's not right. See, it should be 7, 8 something. There.
All right. I can do it.
You told me it was 7, 8, which I think is correct. Oh, we're getting into our limit.
79.50.
What? How is that happening?
Not triggering properly.
What?
I think this, I'm not sure the scope is triggering properly. Is the can you still hear the relay going? Or?
Yeah, it's definitely all messed up. Here, I'm gonna go back down. Just see what's going on here. It's kind of all. There we go. So that is half. Huh? What's going on there?
You got me confused. So
Yeah, I know.
I don't know what I'm doing.
It's okay. If that's... Well, I really gotta adjust the duty cycle to get that right. Let's just go back up to the... What, 7.9? Huh?
Oh, 79.25.
Yeah.
Or 79.50. 79.50.
Not reaching that limit. Okay, that would be quarter. It's pretty close to quarter cycle. Really need the frequency to go up a tiny bit, almost looks like. I don't think I can. I think I'm maxed out.
All done? Stop working.
Oh. The relay's doing different things. It's doing different things according to the induced voltage, yeah, because it's I can hear it.
Yeah.
Yeah, let's just see what it is. It's not terrible. It's not great, but it's not terrible. It's trying. It's not real consistent.
I have no idea what you've been looking for, but
Quarter cycles.
to me that's a half cycle.
It
That's not a
is.
quarter
I
cycle.
know.
I don't know why you keep saying quarter cycle. I'm
Well,
totally
that's
confused.
what I want.
You want to just go from here to here.
Yep. But I can't.
Yeah,
We're reaching some pretty high limits.
Yeah, too fast.
We could without the relay. We could do it with the with the FET.
Yeah.
So we could try it. Not gonna hurt anything.
No.
Back to ground. I can do that with that FET. Just to see what happens. I'll just try it real quick. I'm kind of curious.
Yeah.
I have no idea if I can get that to switch properly like that, but I think I can.
You probably can.
So I'm gonna go. So here's the output. And then the red one. Oh, I get so confused. Okay, this needs to go. This needs to go ground. That needs to be grounded. Nope. I need to think for a second here. That's going to ground. That goes through the coil to the positive voltage. Okay. So out through the coil to the positive voltage. Okay. I got this. I almost know what I'm doing. And this goes to ground. So now we're pulsing through the FET. Oh. What's up with that? I have no idea.
What frequency at?
750. Let me change the duty cycle down to 50.
Is it getting hot?
No.
That's your quarter. Close to your quarter.
Yeah, it is. And that's the frequency that we should be at.
Okay.
So that means the relay is bouncing like crazy,
Yeah,
probably.
Yeah, probably is.
Maxing it out.
Yeah.
But this whole thing does not like being across that.
No.
How is it across that? The FET should be open right now. Am I inducing backwards current through that thing?
Maybe. I don't know.
I'm sorry, I stopped it.
Yeah.
Just want to measure. We're at 10. So we're going back. We're going backwards. Do I have that right? Maybe I got that backwards. Source and positive from the output. It's my load in between, and then going to ground. That should be right. I think it is right. Look at the current. How is the voltage going? How is that happening? How is there almost no current, yet the voltage is going from, I don't know, 8 volts, the battery voltage, all the way down to nothing, like negative a bunch.
Yeah.
What's going on there?
Free power, man.
Yeah! But there's no current.
Yeah.
So now I'm confused.
Well, just show it to Tin Man. He'll figure it out.
Wow.
Sorry.
Oh, that has to be the flyback.
Yeah.
There's almost no input for that.
Yeah.
There is, but almost nothing. Look how
Yeah.
small it is.
Yeah.
And it rings. Look at it.
Yeah.
So I need to switch it on faster.
Faster.
Not higher frequencies, faster.
Yeah.
There we go. Now that's our quarter wave I was looking for. I mean that's a quarter wave if I ever saw one. Sure looks like quarter wave to me.
Looks like a half wave to me, but I don't know what you're thinking.
A half wave.
Yeah. That's what it looks like to me.
And we're starting at 9 volt. And we're letting it go, and it's ringing down to this negative voltage, and then we stop it.
Okay.
So this is not the top of a peak. This is the battery voltage.
Okay.
So the battery voltage turns on and lets go, and that's the peak.
Mm.
So like if I change this to, well, I'll just do it on the fly here. So if I change this, change the big numbers, boom, boom, boom. See it?
Yeah.
So this is the battery voltage.
Okay.
See, that's quarter wave right there.
Okay.
From the battery voltage down to the peak.
All right.
Yeah? No? Makes sense to you? You're confused?
It doesn't make sense to me, but that's okay. If you know what you're doing, go for it.
Well, let's talk about it, because if you're confused, this is bad. So I got 9 volts.
Yeah.
It starts at 9 volts.
Right.
And then I let it go and it swings negative to, I don't know,
Right.
20 volts, 15 volts.
But it's not. 7950 is 1.5 waves at the resonant frequency. So I don't know where you're getting quarter wave.
Well, let's talk about it. If I got a wave, it's like this.
Right.
Right, and this is 6 kilohertz.
5300 in our case, but yeah.
10 kilohertz, okay?
Alright.
And if I were to measure from here to here,
Yeah.
it would be, hold on, 2.5 kilohertz. Okay? Quarter wave. And what is it? It's faster. It should be a higher number.
Yeah.
Yeah, okay.
So,
So it'd be multiplied by 4,
right.
divided by, just
Multiplied by 4. Okay, so
So this is 40? Okay, then here's the next question.
But it's I do it by intervals. You're doing it by frequency. I do it by intervals. But anyway, yeah. The interval from here to here is 100 microseconds. Here, from here to here is 25 microseconds.
Yeah.
Okay.
Okay. So if I were to want to turn this on and off here,
You do 25 microseconds.
but the problem is actually
Why do you want to go from there to all the way to there?
because that's the,
Okay, so then that would be 12.5 kilohertz.
yeah, that's the number I'm trying to find here, which is that number right there.
No, that's the wrong number.
Okay, well if this would be 12.5,
Right.
then what would that be?
66, 50 or whatever it was
Okay.
I calculated before.
So confusing. Totally confused again.
Uh,
But that's okay. Because I'm thinking about it.
That's
I'm
all right.
thinking about it in a different viewpoint than you are, and that's why we're getting confused.
yeah, I'm sorry.
I'm looking at
not
it one
trying to
way.
be- I'm not
Hey,
trying
don't
to
be so
difficult.
freaking sorry, Richard.
Okay,
Slacker.
5,300. $66.25.
All right, 66.25.
Quarter wave.
Okay, there's 66.25. Looks exactly the same, except we're a little longer now, probably more closer to the quarter.
I don't know. That's according to my understanding.
Why would that do that? That should start from a stop. This should start from a stop and swing down to the quarter. If we're doing this right, you know what I mean. This
Yeah.
should, because that's what happens. So let's try this. Let's just go down to 50 hertz.
Oh, 50 hertz.
So this is what's happening.
Right.
So where's my? So this is what we see then. We got freaking time again. I need to fix it so I can read it and you get lost. Okay. Oh, that's only 2.5. What happened there? Something completely different now. That ring is 2.5 now.
Okay.
It's different than what we were reading earlier,
Yeah.
which is a problem.
Yeah.
It's 2.5. Our frequency is set at 50 hertz.
Yeah.
Does that change if I change this? No, it's still ringing like that. Still the same.
Yeah.
Alright, so that's interesting by itself.
Yeah.
Now it's 2.5, so let's recalculate.
Okay.
And actually, you calculate, I'm measuring.
All right. So quarter should be 31.25.
Okay. That's my quarter right there.
Right.
And it says 10 kilohertz.
Yeah.
That's where we're
Right.
me and you are both.
Yeah.
So we need to figure out how we're looking at it so differently, because
Right.
that's different. So
Right.
so-
Because this is 1 1/4. The 31.25 is 1 1/4.
oh, see.
So if you did 1 1/4 here, you should come up with this number.
Okay, so if I do 1 1/4, let's just go this way. There's 1 and then 1/4.
Right.
It's 1 point. Let's call it 2. So that's not right either. 1 1/4. That's why I'm lost.
What did you get? What did it say? It is.
1 point. It's almost 2.
How can this be 25 and that?
I don't know,
Oh, okay.
because something that you're doing and I'm doing is different here. Whatever it is. So one cycle. Oh. Yeah, one cycle.
Yeah.
We'll call it 2.5. It's a little
Okay.
shy, but my measurement's not perfect.
Oh well, 1. Yeah. Okay. All right. I can tell you what it is. Hold on a second.
So 1/4
Yeah. Oh, yeah. Hold on. 25.
has to be a higher frequency than that.
I got it.
It's actually times 4. It's times 4. It's That's what it is. That's what I wrote down over there.
1875. One, yeah. One and a quarter should be around 1875.
1,800. 1 1/4 should be. He says 1 1/4 should be around what?
1900.
Yeah, yeah, in that range. So then, if I were to switch it, if I were to want to turn it on and then let it ring and catch it at the bottom.
Right.
Well, maybe in order to do what I'm thinking, if it starts here, unfortunately, it doesn't really swing up very much. See, when it turns off, it barely goes up,
Right.
which throws us off because that is like missing.
Right.
So now we're going from there down to here.
Yeah, we'll dial it in on the scope, see what it is, but it's not much. It's like
No, it's fast though. It's up in the tens. We gotta be 5. It's that. Let's look at it
from there. What's that?
Yeah. 6.8. So that's that.
Okay.
That's that number that we were at that you had pulled out earlier. 6926.
6950.
Yeah.
Yeah.
So that's it right there. So in my mind,
that's a quarter.
Yeah, but that's really, I guess,
it's not really a quarter. That's why you kept throwing me up.
It's really a half.
Yeah, it's really a half. That's what I kept saying.
Actually, it's not even a half. It's more than a half.
Yeah, a little bit more than a half.
But that's just showing me off that it's not ringing like we were seeing in a ring like earlier.
Right.
Earlier we put in 9 volts and rang
200 volts or something.
Yeah, and now that don't happen the same anymore because of how things are set up.
Right.
That was exhausting.
That was easy.
That was exhausting.
That was easy.
It was easy. It was easily exhausting too.
I was just making a joke, buddy.
Well, okay. So let me think about something for a second here. If that's the case, okay, if that's the case, then I need to take a nap. Okay, that was mentally straining there. That one. Okay,
I was up till 3 o'clock. I'm all in for a nap.
I know. I was up with you, but I didn't get up as early as you.
I got up at 6.
I got up at 7. That's reasonable.
Yeah, that's
for
not
a
bad.
young guy.
Not bad for a young whippersnapper.
Oh wow.
Them old guys, they're tough birds.
Tough birds.
Tough birds.
We need to see if the capacitance acts the same as what we had last time with the internals like we did.
Yeah.
We need to see if that changes or if that's the same.
I got no idea.
I need to charge cap through this at its proper frequency and film that so that I can skip that.
We don't have to do it. I mean, we can take a break and, I'm going to leave in a couple hours anyway. It's no big deal. You can
take a break. Can't take a break.
Take a refreshing weekend with your wife and kids, and then.
When does that happen? That happens after 5 o'clock. This Friday, we got the rest of the day. I got a lot to do.
Oh, okay.
Slacker.
I'm a slacker. Yeah, I'm a slacker.
Oh yeah, I need a full-way bridge.
I'm sure you got one around here somewhere.
Will I charge that twice as fast? 4 times as fast. Just twice as fast. Because I'm only in one cycle, the other cycle.
Right.
Unless that's not true. Oh, it has to be true because it has to go past the negative in order for it to charge that direction.
Yeah.
And it doesn't do that.
Yeah.
Does it?
I don't know.
My poor little cheesy fan. So you think it'll run? I need higher voltage and I can switch it at that lower 5.3 pretty comfortably.
Yeah.
And it doesn't ring very high, so I can go up to 30, 40, 50, 60 volts, no problem.
Yeah, try it on 30 volts.
I want to see if it runs on the relay, you know, like just regular running.
Try
I'm
it
very
on 30 or 40
I'm very
volts.
confused.
Try it on 30 volts and see what happens.
Oh, trust me, I will. That's a little high. It's perfect. Let's figure out where we are here. This is a mess.
Okay.
This goes over here to my stay.
Magnets are handy, aren't they?
They are. Yeah, they are. Let's just take that off. Take that off. Got our
Magical read relay.
read relay here. That's that.
Is our resonant frequency now 2500 though, or?
I think it has to do with the junctions in here and something
okay,
weird.
yeah, okay.
We'll check it again, but I'm pretty
Yeah,
sure
it's 5300.
still the same.
Yeah.
It was doing some weird things.
Yeah. All right. I agree.
So that's that. I don't hear that switching, but yeah, it is.
Okay.
All right.
Good.
Now we'll go back through our cheesy fan. We need to go. That coil, okay, is there. This coil, this actually needs to go through the switch. And then we need to go back to the battery. Back to the battery. Where the other side of the battery is supposed to go to? Oh, this one. Here you go. I got this. I think I can. I'll put this on negative, I guess. And this on positive, I guess. We'll see where that is, I guess. Can't see what's going on here. Is it pulsing? I think it is, I just can't see it. Is there pulses in there? I don't think so.
Relay
It's only on
failed.
50 milliamp.
Relay failed, or?
No, I just probably got something connected wrong. There to there, that goes through this, through the switch,
Hi, Daddy.
back to there. Hey Riley, you come out here to figure things out?
Yeah.
Don't
We
need
have
not.
to let the purple keynote charge.
What?
I read my book. It's the purple keynote. The pink one.
Okay, something is strange. Let's check our battery. Seems like it's a little off. Unless it's not.
So what
Nice.
are you
Triggering.
doing?
There and there. No battery voltage. How about here and here?
There's 6.
Okay, now what about here and here? Can you turn on that that output button on the signal gen?
Where is it?
Yeah, that one. Okay. nothing there coming out of this thing. One cookie just fell off the battery. Relay died, maybe. Oh, you know what it is? Duty cycle. Alright. Put this back at 50 for the moment.
Okay.
There we are.
Alright.
Close. Timing might be all wrong here.
Yeah.
Let's see where we are. We're on that side of the cycle. Theoretically, that should...
Try changing your frequency on your frequency generator.
Let me try this instead.
Are you in that? You in that? Oh wait, no, I thought you were in it.
Hello, kids. It's barely running, but at least it is. It has like the same effect in motoring. It doesn't go at all.
You could try changing your 5300 hertz and see what it does.
Funny. I got phone spinning.
There it's running.
Yeah. What frequency?
300.
300.
This way?
Stopped. Oh, there it goes. There it goes.
Duty cycle.
Yeah.
Because it works both ways. Which we kinda knew that, but hey, can you guys not fall off there? Just get off for 1 second. Get off for a second. Okay, don't raise this to the top.
I wasn't. It was already up on the top.
Okay, leave it all the way down so you don't fall and bust your face. Hey, Lily, come sit on this.
No, it's not very good.
Well, then don't bother her so she doesn't fall off. I don't need nobody to fall off. Yeah, see ya. Bye-bye. Thank you. Ridiculous, that one. Ridiculous. Sometimes I just shrug my shoulders and say, ridiculous, and I go on my way. Russ or Richard, did you go to the Consumer Electronics Show? Nah, we ain't got time for that crap. Actually, it would have been a lot of fun, but no, it's probably like a couple $100 to get in for all I know. Nobody gave me a free pass, so we didn't go. Alright, well, it does not run.
No.
Which, in my mind, was kind of expected.
Yeah.
So, because it's the same in as out, in that case, motoring or generating,
Yeah.
it's very similar.
Yeah.
So there's not enough current going in the right direction. It's just oscillating in there.
Yeah.
So now I want to go up to like a higher. I wanted to go up to a higher frequency. That has to be offset for that to happen. All right. What time is it? Is it lunchtime?
Yeah, mommy's making me go cheese for herself and get mom and get
It's 11:30. It's time to eat some food, I think.
Yeah.
Well, let's see real quick at 300 hertz what this actually looks like. Kind of curious. Yeah, a little current spike's going up there.
Yeah.
And it's ringing there.
Ringing
At that
again.
6 kilohertz there. Let's see if it's actually 6.
Should be 5300 actually, but
No, the self resonance.
oh,
It should be back to. It was at what? 50. Oh, right. It was a different frequency than our first original frequency.
Right.
Yeah, it's about back where it was.
6 kilohertz.
5.3, 5.4. Yeah. Alright, peoples, we're gonna grab some food. Be right back. In a little bit.
Disconnect your battery or just...
Yeah, read switch disconnected. It's okay, I think. Weebee's back, yo. In a little bit. Weebee's be back, yo, in a little bit. Let me grab my cup. sorry.
Ow. Oh,
Got my foot stuck in the door.
that's not good.
Well, it's my shoe. Alright, let's fire it up, son!
Are we still live or?
Uh-huh. We are on the air, as they say. On the air. We are currently on the
I don't
air.
know about you, but my feet are on the ground.
No, we are on the air. This time I'm not going to use a diode. I'm just going to use this switch and see how she goes. That'd be interesting. See if there's any, probably not much difference, but
Yeah.
seems like it's always lunchtime there. Shuba says, yeah, well, I like to eat. Get over it. Oh, Shuba, it's always lunchtime. He says he thinks it's always lunchtime. Okay. Let's put this under there. Maybe like that. That's too far. Oops. Wait, how did I do this last time? This wasn't this far out. Oh, I put it on that side. That's why. Okay. Power! Give me power supply! Give me power!
Alright, you got power. Now what?
Well, now I'm confused. Nothing happened.
It's virtual power, that's why.
Oh, snap, son. I got my loops in a tangle. You stay over there. You stay over there. Red. Black on red and red on black. That's right, right? Whoa, she's going. And they're off! What's happening? I don't know. Can't figure it out. What RPM we at?
Where's your RPM meter?
It is nowhere to be found. Okay, you ready for this calculation? Multiplied by 60. 23 times 60.
23 milliseconds?
No, hertz.
23 hertz.
Times 60.
1380.
1,380.
Yeah.
Okay, let's put our capacitor on here. It might charge backwards. We'll just find out. Not sure what's about to happen. It's at 7 volts. Okay, so that's interesting because I'm at 300 hertz right now.
Yeah.
I gotta watch my voltage. Remind me to watch my voltage.
What's your voltage?
I don't want to go above 100-ish. So let's put this at 5.3 kilohertz. Let's make sure that it is actually running right. Thirty cycles at 60. Put it back at 50. Whoops. 5.3 kilohertz. Plug this back in. Okay. Huh. Oh, I don't know what that means. Oh, I see what that means. Let's try putting the diode back in there. Maybe I need the diode back in there. To make that work. That charged up very fast. What happens if I bypass the relay? Oh, just went off the charts. Sure does make a good high voltage generator.
Yeah.
How do I discharge? Gotta discharge. I want to discharge cross coil. Guess I just need to short these out. Oh well. I need a little bit higher.
What are we doing?
I don't know what you're doing.
I got interrupted with a chat.
Yeah, I know you did, you silly man.
Sorry.
Prioritize. I know where your prioritize are. And that's cool. Okay, so look. Just giving you a hard time.
Okay.
Okay, so... Wow, that resistor burned. So I'm going to turn this output on.
Yeah.
It's that base. It's negative, so it's 0 volts.
Yeah.
You can hear it dragging out a little bit.
Yeah.
Okay.
Volts, 70 volts, 80 volts.
What was that? Was that my current?
I heard something, a little beep, but I don't know what it was.
Okay, so there's that. I will discharge this again.
Yeah, it's negative.
And we're just gonna basically bypass the read switch.
Okay. Or it really bumps down.
There's 80 volts.
Yeah.
So basically we need to compute all that and try to quantify that again, see where we sit. So we kind of did this once before at the different frequency. That's a 500 UF cat. That's a pretty decent sized cat. I need to flip, it's only charging, okay, let's take this off. I was hitting the switch, so now we're not hitting the switch anymore. It's still only charging on 1/2 cycle. So then let's discharge it. Okay, let's try it again. Without the read relay. There we go. And then with the read relay, it's definitely a much greater time frame.
Yeah.
Oh, but right. So we need to go up much higher. I think I need to take the magnets off. Ouch. Bit my straw. Okay. Whoa. What's going on? Oh. I see what's going on. Okay, that's a problem.
I can't find mommy. It's not upstairs and not downstairs.
I don't understand that, girl, some days. But that's okay. I don't need to. Alright. So, that's kind of a problem. It's producing a voltage which is arcing over in the read relay.
Yeah.
If I turn this on, and now it's okay. And we're at 300 volts. Yeah, okay. Can't go that high. That's RMS. Holy cow. That is such a high voltage. It's 100 volts per division. Okay. Why is it still doing that? That's very strange. Look at these waveforms. Square waves.
Yeah. Wow. Because of it arcing over, or because of what?
Can't figure it out just yet. But it's only charging in this time frame. So is that the diode conducting?
Could be.
But the current is steady the whole thing. It's an arced current. Yet the charging is square waved.
Weird.
It's odd.
It's got to be the diode turning on and off. I don't know why. I don't know what. Maybe those spikes are causing the diode to switch. Are they lined up? The switching is lined up with the spikes.
Yeah. Why would that do that? I have to think about that. Ow! For a second. That is a bit odd to me. If I can't remove it. I'm gonna try something. Let's turn this down. Turn this on. But I need to put a resistor. Let's put this one on there. Switch these probes so I can see the difference between the others. Okay. Now our switch, we can turn it on. Milliamps. How many milliamps are we supposed to be able to handle?
Half an amp, I think, on that one.
Okay.
What? It was being triggered by some kind of a spike.
It's only happening when it's charging.
Huh. Only when it's charging. So, when it reaches a certain breakover voltage, then it kicks the diode, or what?
Well, it's 200 volts. Maybe my read relay is not firing. No, it has to be firing. Maybe it's breaking down. Hello, Riley. What you doing?
Kindle cooking it how I can do that.
Okay, I think it's just breaking down. Let's see, bigger resistor. There, that would work. Let's try that.
Sorry about that.
Mm-hmm.
Hey.
Freaking love. You're in love, man. What are you going to do about it?
You tell the whole internet. Okay.
Ain't nothing to be ashamed of, son.
No.
Okay. Whoa. Is that right? 2.7 volt. Oh, yeah, that's right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 super caps.
10 super caps.
Times,
one
times,
farad.
times 2.7.
How many farads are they?
4.7, but 2.7 times
Whatever I said.
10, 27 volts.
Alright, so I can't go above that.
Alright. And we got basically 500 millifarads of capacitance. So you're charging half a farad at 27 volts, up to 27 volts.
Just bypass this for a second. Oh, yeah, look at that. Here's the meter. 4.7, 4.8. So it is working right. 4.9.
Yeah.
I'm gonna put it back on the pulsar. And I need to be careful with my maximum voltage. I'm on 100 volts. So I'm on 100 volts, and
The purple one here is the voltage, right?
yeah, but the breakdown voltage of the reed switch is what that.
200.
I think that's what we're seeing, and it's very strange that it's a square wave.
Yeah.
I don't quite get that exactly,
I don't either.
but it is a square wave. So I can't really go much more without. There, it's charging up now. See it breaking down?
Yeah.
5 volts. 5.1. Here, speed up.
Yeah. Yeah, definitely sped up and slowed down.
Now, if I short it,
It really bogs down.
that motor's free spinning over there.
Yeah. Yeah.
Alright. See how the current is?
Yeah.
So when it's breaking down like that, it seems like it slows down more.
Yeah.
So when I go down here, just make sure it's not breaking down. Just run it. When I run it like this, it's still a little too
Still
fast.
breaking down a little bit.
Unless there's something else going on, I don't quite understand what it is. Remember, our peaks had to be higher than a certain value. Remember?
Yeah.
And look at where. Oh, those volts are huge, though, compared to our 5-volt cap.
Yeah.
A 5-volt cap is like nothing. But see, it's not charging there at all.
Right.
There, now it's charging.
Yeah, it's
Now we're
break
starting
down.
to.
Yeah.
Is that breakdown? We gotta figure out what that is.
How are we gonna figure that out?
What's it look like without the?
I gotta go brush my teeth. I'll be right back.
Okay. So that's what it looks like without the switching. So that's what it looks like without the switching. What's the thumping noise? Sounds like an empty plastic bottle banging on the table. This fan's running. Might be what you hear. So there's an impulse, and then there's actually a constant current. There's an impulse of about 56 milliamps, and then there's a constant current. So measure, let's go to test to find the inputs. Voltage, current's going to be blue, and obviously between the cursors. So we'll go from
there to there to. Hold on, I gotta answer my phone call here. I'll be right back. Hello. Okay, what the heck was I doing? I was quantifying something. I was trying to take a measurement. I need to take the measurement about right here. Now I want to go to test, and I want to know 30.39 milliwatts. I'm going to capture that again and make sure that that's actually about right. Why am I not getting this thing? Current is not reading. There it goes. Alright, this is going to be... Oh! It's going to be a very hard measurement. Let's see what it says anyway. So measure, test. It says 111, which is quite a bit higher, and yet it's like hardly even bogged down at all. It's pretty cool. Take another one. That one also says like 160 something. 116 I mean, so that's probably fairly accurate measurement. Now I want to take a measurement of the current like this. It's just maybe I did something wrong, but let's try this again. So I'm going to measure this now. Test. True power, approximately 25 milliwatts. So that's 111 milliwatts versus 30 milliwatts. Now I have to try to find a way to define my input a little bit better. How can I create... I need to be able to create constant torque on my shaft at constant RPM. I have no idea how to do that at the moment. It does slow down a tiny bit. Seems I can't switch this fast at high voltage though. Well, there's probably bad measurements. However, and I haven't quantified this because I gotta figure out how to do that.
Yeah.
But it's a difference between somewhere around 30 milliwatts and 111 milliwatts worth of charge going in.
Yeah. So,
But one's rotating almost at no RPM, so I can't hardly even figure that one out right now. And the other one's spinning like real fast like this.
yeah.
So
So
I can't quite determine what's
the
what.
30 milliwatts is when it is charging?
They're both when it is charging.
Oh.
But the difference is that this one is when it's just shorted out, this one when it's pulsing.
Ah.
Whether that's a bad measurement, I can't tell you, but It's an interesting one nonetheless.
That is interesting.
But it's spinning a lot slower, so we have to...
Yeah. So you gotta take that into account too.
Oh, now that one shows a totally different thing now that I'm zoomed in on it. Which probably might be more correct, I don't know. That's a, let's see, 20 milliamp per division right there. I could try to remove all the noise, I guess. Oh, right. That's because I'm using a different frequency now. If I go back to 5.3, take that measurement. Now we're at 175. Oh, okay, so I think it's fine. So there's a little cogging there.
Yeah.
But it's not much. It's like you can hear it.
Yeah. Yeah, I can hear it.
But
Wow.
and that guy's just spinning away over there.
Yeah.
It's like a dramatic difference. So
Dramatic.
I got to figure out a way to have a constant torque, constant RPM. I got to figure out.
That machine over there. You need something like that machine over
I
there.
know. I do need something similar to that. I mean, these should be pretty good measurements.
I mean, you could make up a little version of that if you had like a DC motor and you run it off of a power source that was, you know, coming from DC, and you know, I don't know how.
If I put a belt on here and I had a geared down motor, which I do,
Yeah.
that would be, I could quantify the input a little better because it would be a little higher.
Yeah.
Then I could determine the difference there, I think.
Yeah.
So like,
It must be blasting her ears out when she does that.
I don't know. So like this. Why is that so high right there?
I have no idea.
Okay, so this is from here to there. Okay,
Yeah.
I'm gonna test it. It's running a lot slower.
Yeah.
So it's about 35.
It's not all that slow, but yeah.
35. No, not now.
Yeah.
When I short it out.
Oh, okay, yeah.
It's like
35 milliwatts.
Yeah.
Yeah.
And then you do this.
Careful your wires there, buddy.
So now it's probably gonna clip a little bit. Oh god, that's a terrible measurement.
Yeah. You didn't like those spikes, I guess.
Hold on.
Where are your cursors?
Yeah, it's on cursors. There to there. What's up with that? I didn't have that bad of a measurement. Oh, I see. Hold on. That's a true measurement. That's a correct measurement. See, I gotta get to one of these over here.
Uh-huh.
That one wasn't putting anything out. I don't quite fully understand that yet. What's really going on there?
I don't either.
There we go. 192, even though it's clipping. It's probably somewhere in that range.
Wow.
That's a big difference.
Yeah,
So I really got to figure out the best way to quantify my input. Because I really do want to know if there's a benefit to this or not.
yeah.
I would expect there would be a benefit because it kind of resembles the result we want. It definitely resembles a similarity to a result we want,
Yeah.
which is a great thing,
Yeah.
actually. That's a really different
Yeah.
way of doing things, so to
Well,
speak.
yeah, totally different. Yeah.
Because you can't usually get to these frequency ranges and play around with this thing. Maybe there's harmonics you can play with. I don't know, but
Yeah.
in this case, we can actually get to it
Yeah.
with your wonderful reed relay,
With your wonderful pancake course.
your wonderful magnets that disrupt everything in my shop. Did you see that video I made? Right, with that magnet sitting on the couch. It's insane.
Yeah, that is insane. Well, you can go big or go home, dude.
Yeah, well, we did that. We're still doing that.
Oh, that.
So a lot of angry red spikes on the screen.
Angry.
I'm wondering which scope it is. Alright, I'm gonna go do a thing. Bring.
You can tell him what scope it is.
You wonder what my scope it is? My scope? I think he's talking about his. I think he got one.
Oh.
Maybe he's talking about mine.
I don't know.
Anyway, we're gonna run some. I gotta run an errand, and then I'll be back and probably continue this. I'm gonna have to define a way to run the input way more accurately. Try to define charge constants and crap. So we'll be back. I'll be back.
I'm leaving.
Yes, Richard is heading out. Mine is a MDO 4024C.
24C.
Alright, streaming off. We'll be back. I'll be back. Richard will be back online.
Yeah.